Welcome to the part 3 of this video lecture series of UPH004 Applied Physics course. In this part, we'll talk about the interference due to a parallel thin film. So this is the part of the syllabus that we'll cover in this lecture, parallel thin film. So to start with, the interference in parallel thin film or parallel plate. First, one idea we have to understand is called the idea of optical path. So what happens is, in a medium of having a refractive index mu, when light travels, then the actual geometrical path that the light travels is not same as the actual path traveled by the light. So there are two things. One is a geometrical path or distance, and another is a optical path or optical distance. For example, let's say there is a light source here, and from this light source there is a ray of light going to a point P here. So the physical path or the geometrical path that the light travels from the source to the point P is SP. However, if the refractive index of this medium where the light is traveling is mu, then there is another definition of the path. So this is geometrical path, and that optical path would be mu into the geometrical path, mu into SP. So this is the amount of distance that the light is actually traveled. This is called the optical path. So we have to remember this to start with. So now next we have to understand what is a parallel thin film. A parallel thin film is a film whose thickness is same throughout the film. For example, the thickness here and thickness here all are same, let's say. In that case, this would form a parallel thin film confined between a medium 1, between this there is another medium 2. So this medium forms the film, and this would be a parallel thin film when this thickness at every place is same. It could also be that this medium is not same as the medium here. So that could be a separate medium. Let's say this is a medium 3. So for example, this could be air, this could be magnesium fluoride, this could be glass. So such a situation happens on the surface of a glass. This parallel thin film is made up of this material, magnesium fluoride. We'll talk much about such a system. Now with this, let us look at the situation of a interference occurring. So before we start talking about the interference, let me introduce two new terms. One is called localized interference and another is non-local interference. The example of the non-local interference would be Young's double slit experiment. So what happens in a Young's double slit experiment? What happens is that there are two slits. So parallel lights are coming in, monochromatic light, let's say of the same wavelength lambda, and then from this slit the two rays of the light goes and meets on a screen. So here is the screen. So here are the slits, this is screen. So on this screen you see interference pattern. Now if I put the screen here a little bit in front or here, then accordingly the interference will happen on this screen. The interference pattern that you see on the screen is due to a path difference that gets created here. So this is the path difference as the light moves from the slit 1 and slit 2 towards the screen. And this path difference determines what kind of fringes or interference patterns you will see on the screen. At every point the path difference is different, so accordingly you see fringes or interference patterns on the screen. Now see, the sources are here and the path difference is created at this point, and interference is happening at a distance on a screen, and that's why we call such interference phenomena as a non-local interference. Means sources and where the interference actually happening are separated. They are not near to each other, they are far away from each other. However, for the localized interference, what would happen is that the source where the path difference is getting created, there itself the interference patterns or fringes will be formed. So interference occurs just near to the sources where the path difference is getting created, and that type of localized interference phenomena we see in case of thin films, whether it's a parallel thin film or a wedge shaped thin film. So for localized interference, the examples are interference that you see in case of a thin film, and we'll talk about this further. So what is happening is, given a thin film, medium 1, medium, let's say this is also medium 1, this is medium 2, and this thickness is very, very small, of the order of micrometer or even a few nanometers. So the medium 2 is enclosed by a medium on the two other sides. So this could be air, this could be, let's say, glass, and again air. So what is happening is, when a light ray falls on this surface, then one part of it gets, of course, reflected and another part gets transmitted. Now then again, this transmitted ray, when it comes on this interface, then one part of it gets reflected and another part gets transmitted again. So when this reflected ray meets this interface, then some part of it gets again transmitted and some part of it again gets reflected, and this continues. One thing that you need to also understand, as these multiple reflection and refractions are happening, let's say this is ray 1, this is ray 2, this is ray 3, this is ray 4, 5, 6, 7, 8, and this will continue. Now one thing that you have to understand is that after this subsequent reflection and refractions, the rays which are coming out, their amplitudes would decrease substantially after each reflection or refraction. So the ray 2, for example, the amplitude would be much more smaller than the ray 1, because some part of it got refracted as the ray number 3. So the intensity of the sixth ray would again be much smaller than the intensity of the ray 2. Similarly, for the ray 4, the intensity would be much smaller than the ray 3. Then similarly, with each subsequent reflection and refraction, the intensity of the different rays would get diminished and slowly. So what happens is, after say 1 or 2 reflection or refraction, the intensities becomes too much low and you don't actually have to consider them for your further analysis. So let's consider only the first 2 rays which got transmitted back into the medium 1, and these 2 rays are second ray and the sixth ray, right? So for these 2 rays, as they are moving towards this direction, there is a path difference that they have traveled. How much is the path difference? So at least you can say that when these ray 2 gets reflected from this point here, then ray 2 is traveling less than the ray 6, because there is an extra path that the ray is traveling from A, then to the point B here, then to the point C here. So this path difference is actually going to determine if these ray 2 and 6 comes and meet and do the interference, what kind of interference pattern one would see. Now next we will try to calculate the conditions for the interference, and for getting the conditions, the most important step is to calculate the path difference between different rays which form the interference or to undergo interference. Now to calculate the path difference, here we come back and look at this detailed picture here, and here all the steps are mentioned one after another, but let us elaborate on this and see what happens to the path difference. So I have got this figure here onto my worksheet, and let's calculate the path difference. So the path difference between the ray 1 and 2, because these 2 rays are parallel to each other, the path difference would be coming from this ray 1, which is traveling from A to B, for the ray 2, this path is ACD. So the difference between these two would give you the path difference. So optical path difference is AC plus CD into mu minus AB, where this mu is the refractive index of this film. Now also what we have here is this incident angle is I, refraction angle is R. So from the geometry itself we can say how much is AC. So if we extend this part here, let's say this is some P, so AP would be is equal to AC cos R. Now AP is the thickness of the film here, which is D. So this is D, AC cos R implies AC is equal to D by cos R. Now here AC and CD are same, so we can write this to be is equal to 2 into D cos R into mu minus AV. How much is AB? Now again looking at this triangle here, AB is equal to AD sin I. This angle I is same as this angle from the properties of the triangle. How much is AD? AD is twice of AE. How much is AE? AE is D10R, where D is this distance into sin I. So that gives you AB is equal to 2D10R mu sin R. So let's put it back there into the AB. So we come here and write this expression. So from here you can simplify and get this is equal to cos into R. So the optical path difference is equal to 2 mu D cos R. Now there is another very important point that we have to think about is the Stokes relations that we derived in and discussed in another video. From the Stokes relations, what we have to think about is, as this ray is getting reflected from this point A, what is happening is this ray comes from a rarer medium and gets reflected from a denser medium. Then there would be a phase difference between the incident ray and the reflected ray. So the ray, and that phase difference is pi. With respect to the incident ray, ray 1 has a phase difference of pi. So here ray 1 has a phase difference of pi with respect to the incident ray here. Then on the other hand, the ray that gets transmitted and then subsequently gets reflected from the point C, it doesn't get any phase shift. So first, phase shift only occurs during reflection. So the ray AC would not have any phase shift or phase difference with respect to the incident ray. The reflection that is occurring at the point C, there is no phase shift or phase difference that gets introduced. Why? Because AC is coming from a denser medium, and at point C it gets reflected from an interface with a rarer medium, air in this case. So when that happens, then there is no phase difference between AC and CD. And then again, when CD gets transmitted and forms this ray 2, there is no phase difference included into this refraction at point D. So ultimately what is happening is that there is a phase difference between ray 1 and ray 2, and that is due to the reflection that is happening at this point A. So if there is a phase difference between 1 and 2, that would also correspond to a path difference. Phase difference and path differences are equivalent. We can convert one into another. So path difference is 2 mu D cos R, and then the path difference that is created due to this phase difference between 1 and 2. So the phase difference is pi. So phase difference of pi is equivalent to a path difference of lambda by 2. So this is the total path difference between the ray 1 and 2. Now for the interference between the ray 1 and 2, this path difference follows the following conditions. For the interference to show a maxima or a bright, then this path difference must be is equal to n lambda. Now if you rearrange these expressions, then what you get is where n are all integer values. So this is the condition for the maxima of the interference. Similarly, for the condition of minima, we have the path difference must be equal to 2n plus 1 lambda by 2. Rearranging this, you get where n is equal to 0, 1, 2, 3, all the integer values. Now, these are the two conditions that one has to remember for getting maxima or the minimum in case of a interference due to a parallel thin film of thickness d and refractive index mu, where r represents the refraction angle, which is again related to the incident angle, and the lambda being the wavelength of the light that was used for the interference. So now with these two conditions for the maxima and the minima, we can go now to look at what happens with the refracted lights. So if you remember here, these 4 and 8, these are the transmitted light. So if interference happens between these 4 and 8, then how would we calculate the path difference? Now the calculations are again straightforward. Here is the situation. This is like our last 7 and 8 ray. This is the original incident ray, and then the multiple reflection, and then again reflection happens, and ultimately you get the ray 8, and from here after refraction at the point C you get ray number 7. So to calculate the path difference between the rays 7 and 8, what we have to look at is that with respect to the ray 7, the ray 8 has traveled extra CD, then DE, and the ray 7 has traveled during that time the path CP. So the path difference would be CD plus DE, that is traveled in the medium with the refractive index mu. So the optical path difference between the ray 7 and 8 would be given by mu into CD plus DE minus this distance CP. Now to convert this CD and DE and CP into our known terms, that is the incident angle I or the refraction angle R, and then the thickness D of the film, we follow as we did in the last case, and like this one here, and from some of the geometric principles of right angle triangle from here, this picture, we can come to this, that the optical path is given by 2 mu d into cos r. So all the steps are described in this slide, and if you go carefully, then you can find out that the optical path difference is equal to 2 mu d cos r, as it is shown here. Now then, one last important thing that has to be mentioned here is, so with this optical path difference 2 mu d cos r, we have to think about what would be the condition for the maxima. As it can be seen here, that is condition for the maxima, that means ray 7 and ray 8 here would meet and interfere and produce a maximum or a bright spot when path difference between the 7 and 8 is given by 2 mu d cos r is equal to n lambda. One thing that you can see here is there is no lambda by 2 term, which we saw in the case of the interference due to the reflected light. Why? Because here, in case of this transmitted light 7 and 8, the reflection that happens at the point D and point C, so in both cases, the reflection happens at an interface where the incident beam, for example BC, is coming from a dense medium with a refractive index mu and getting reflected from an interface with a rarer medium outside, which is in our case, let's say it's air. In this case, if you remember the Stokes relations, there is no phase difference between the BC and the reflected ray CD. Similarly, in case of the reflection that is happening at the point D, there is no phase difference between CD and DE, because again the reflection is happening as it is going from the denser medium and then getting reflected from a rarer medium. There is no phase difference created at the point C and at the point D. So that extra lambda by 2 path that was there in case of the reflected light, this lambda by 2 term is not appearing in this case, and that's why the condition for the maxima is 2 mu d cos r is equal to n lambda, and similarly for the minima the path difference is odd multiple of lambda by 2, 2n plus 1 lambda by 2. So again, what is the bottom line? The bottom line is that the conditions for the maxima and minima in transmitted light reverse of the condition for the reflected light. So now here is a point to think about. Given a parallel thin film where there is a incident light of a given wavelength lambda, what you actually would see. So with these two conditions for the case of interference due to reflected light, the parameters for a given thin film mu and d are fixed. Only the r, which is the refracted angle, which depends on the incident angle, would change according to the angle at which the rays are incident on the surface of the thin film. So given a thin film, either this condition would be satisfied, condition for the maximum, or the condition for the minimum. And that's why for a parallel thin film, when monochromatic light falls on it, either we'll see that the surface of the parallel thin film is illuminated with the same color, that means the wavelength, or it will be completely dark, means minimum, no light. There is a complete destruction of a light due to the interference of the reflected light. Similarly, if we look at the transmitted light, that means if you are looking at the film from the bottom, then with these two conditions where mu and d, and depending upon what is the incident angle, correspondingly the refraction angle r, and given the wavelength of the light, either the maximum condition would be satisfied or the minimum condition would be satisfied, and so accordingly either we will see a complete high illuminated bright surface or a completely dark surface. So non-light, either all the lights are passing through or no lights are passing through. So now going back to this, that what if monochromatic source is replaced by a white light? So let's say we are looking at the interference due to the reflected light. So there is a source which is not monochromatic, let's say it's a white light, so lots of wavelengths are there. So when that light falls on a parallel thin film, and as it gets reflected from the thin film, what we will see? Again, the refractive index and the thickness of the film are fixed. It's not going to change. Only what it can change is the lambda, because the source is not monochromatic. There are lots of wavelengths. So for some wavelength, the reflected ray might interfere destructively, and for some wavelength, the reflected ray interfere constructively. So what we'll see is a rainbow pattern. So in certain region of the thin film, we'll see one color, and then there will be a dark area, then there will be a bright area of a different color, then there will be a dark area, then there will be a bright area of different color, and so on. And because this path difference condition, minima and maxima condition, depends on the refraction angle, that means the incident angle in turn. That's why if we change our viewing angle accordingly, or if we change the direction at which the light is falling on the surface, the condition will change. And that's why we will see the color to change, the distribution of the color on the surface of the thin film to change as we change the incident angle, or if we change our viewing angle. So, and this is the reason actually why we see the colors on the surface of a soap bubble changes as we change the direction of our view. Of course, there are other reasons for the color change in case of a soap bubble. For example, the thickness of the soap bubble might change very, very locally. So with this, we end the part of this lecture where we discussed the interference due to parallel thin film. And we have talked about what are the conditions for the maxima and minima when we consider the interference due to the reflected light, and what are the conditions for maxima and minima when we look at the interference due to the transmitted light. And also we discussed what happens when the the light is not monochromatic, rather it's a white light having several wavelengths.